Very good evening, everyone. Welcome all to again the monthly research article spotlight. So the today speaker is Mr. Vivek Yadav. He completed his bachelor's from Sri Venkateswara College, University of Delhi, and master's from IIT Roorkee, and he published one paper in electrochemistry there. And after he qualified JRF in 2019 and joined IIT Madras under Professor T. Pradeep for the PhD. So he will discuss about his recent work which he has published. So over to you, Vivek. And please make sure you complete it in 25 minutes for the enough time for the discussion. Yeah.
Yeah, sure. Thank you very much, Deepak, for the introduction. I believe more people will be joining.
Yes,
Or-
2 people have just joined. 3 more have joined.
Okay, let me present. Yeah, can you see my slide? Is it full screen?
Yeah,
Yes.
it's full screen.
Yeah, thank you very much for the introduction. Am I audible to everyone, right?
Yeah.
Yes. So, coming to today's monthly lecture, I will be talking about my recently published paper, which is titled as Site-Specific Substitution in Atomically Precise Carborane-thiol Protected Nanoclusters and Concomitant Changes in the Electronic Properties. So I will take you to the story of this paper, starting from the very introduction of nanoclusters. Few of the people are new here, although they have heard many times about nanoclusters. But still, I will give a brief introduction where I will tell you that nanoclusters are the entity which lie in between this molecular and nanoparticle region. These are the clusters which are having a metal core which is surrounded by a certain number of ligands. See, and their size is almost 2 nanometer. So whatever is having a size of 2 nanometer is a nanocluster. That is the question. This is the entity which is having a good size. I don't know the exact size, but this we will not call it as nanocluster, because nanocluster, I told you the basic definition. There should be a metal core which is surrounded by some ligands. So with that, this metal core can be of different types. And the ligand, there are many possibilities of ligands. And this metal core can be icosahedral, octahedral, or that kind of things. And there will be a staple surrounded by some ligand. Sorry? Yeah. So what I am interested in this carborane-thiol ligands, because carborane-thiol ligands have given thermal stability to the system. What one of our senior, Dr. Arijit, has also already published many papers. Even in my work, I have shown that it is giving stability up to 250 degrees centigrade. Now, what are these carborane-thiols? Coming to the introduction of carborane-thiols, these are the carboranes where the carbon position is just adjacent to one another. This is orthocarborane. When it is at the meta position, it is metacarborane, and when they are two apart, that is paracarborane. When we will thiolate these systems, we can have different types of thiols, say range of thiols. Like this is ortho 1 carborane thiol. At first position, thiol is attached. This is O9. At the ninth position, thiol is attached. So this is ortho 9 carborane. And there are many more thiols like that. This is meta 9, that kind of things. So what we are doing, these are small, very small clusters. Say this is icosahedral carborane thiol. So what we are doing, we are clustering these clusters together to form nanoclusters, which are having a unique, as I told you, this is the metal core surrounded by these ligands. And special thanks to Dr. Thomas Basse, who is supplying us like good quantities of these thiols so that we can proceed with our research and many more things what we are doing it today. Special thanks to Dr. Thomas Basse. So now I think these carborane thiols and these things are justified. Now I will go to my work. So this work, what we did, we started making nanoclusters using this Busch-Shifrin method. Busch-Shifrin method is the direct co-reduction method where we will take metal precursor, add a ligand, metal thiolate is formed, then we will reduce it to form a crude product, then we will purify it to find the final nanocluster. So in my case, what I have done, I have taken this silver nitrate solution and ortho 1 carborane thiol. See, at this position, as I already told you, first position, two carbons are, so this is ortho-carborane. At first position, this thiol is attached. So this is ortho-1 carborane-thiol. So this is about the ligand. When we characterize this sample, we found that this is silver 17, ortho-1 carborane-12, 3 negative. I will go to the characterization one by one. Initially, we found the crude. Then, first of all, what we will do in nanoclusters, we will go for the UV of that sample. And we found that silver 17 is giving a prominent feature at 400 with a clean mass spec peak at 1312, showing that the composition is silver 17, ortho 1 carborane 12, 3 negative. And the experimental and theoretical, experimental and simulated spectrum matches well. Now, coming to the point, like we got to know from the mass that there are 17 metal atoms which are having 12 ligands outside. But what is the core? What is the structure of how 17 atoms are arranged? For that, we have to crystallize these samples. So we crystallized this sample and we found that this is the structure of silver 17 with 12 carborane-thiol protection. What is unique about this structure? See, there is a metal center, which is surrounded by icosahedral, which is capped with 4 tetrahedral metal atoms. So why this structure is so unique? Because we are seeing 3 different kind of positions where we can try to incorporate other metal atoms. This was the idea where we wanted to do, this was a proposed, that time we thought that let's try to dope it with some other metals. But why doping? What doping will give? So there are many reports from the literature where people have shown that only if they will exchange one metal atom, it will drastically change the properties and even the applications. This is a report from Dr. Buddharaju, which shows atom precision heteroatom core tailoring of nanoclusters for enhanced solar hydrogen generation. Similarly, there are reports where people showed that CO2 to CO, the Faraday efficiency increased from 60% to 90% by incorporating copper in the system, copper in the gold nanocluster. There are many other reports to support these kind of studies. So with that idea in mind, what we started, we have seen that there are 3 distinct positions. So we started incorporation of different metal atoms. So as we started first from gold. And what we see when we are putting gold in the mixture, the UV is shifted. This is not a very good UV. This is the UV of the crude. This is the first UV. I am taking you from this journey that initially what we have seen and what are the final products what we got. So what we see, we saw a shift from 400 to 385. Then we went for the mass spec. And mass spec showed there are some other things also present. That's why UV is not that prominent. But in the cluster region, the only peak is gold silver 16. Only one silver atom is replaced with gold. So I left this question to everyone. What is that position? So answering that position will be the center atom. But we have to prove that. So we crystallize this sample and what we found that the gold is really going and sitting at the central position. This is confirmed from this single crystal X-ray diffraction. Similarly, when we try to incorporate copper in the system, so what we see initially when we added a pinch of copper in this brush shifting method, what we see there is no shift in UV. UV is intact at 400. Then we did the mass spec. In mass spec, we see there are many peaks corresponding to 1 copper exchange, 2 copper exchange, and 3 copper exchange. And similarly, a very small hump of 4 copper exchange as well. So what we thought that copper might be going at the outer peripheral positions, these positions. That's why we are seeing 1 copper exchange, 2 copper exchange, and 3 and 4, so on. So with that idea in mind, we optimize this reaction. How we optimize this reaction? By playing with the amount of copper what we are supplying. So playing with that, what we found that after optimization, we are able to get the one prominent peak corresponding to silver 13 copper 4. That means all the outer copper are replaced by, all the outer silver are replaced by copper in this case. And again, this theory, this simulated and experimental isotopic distribution pattern matches well. Now we have a theory that copper is going at the peripheral position. But to prove that, in mass spec, we can only say 4 copper are replaced. But to prove this theory, we have to go for single crystal X-ray diffraction. So we crystallized this sample as well. And we found that really copper is going and sitting at the outer peripheral position. This makes copper accessible as well. Now, as I told you, we have seen that this center atom, we are changing it with gold. And the outer peripheral positions, we are changing it with copper. Let's try it together. And what will happen? The soup of metals, and then we are reducing it. Then the thiolate is coming into picture. But we are fortunate enough that we got the first trimetallic nanocluster crystal with carborane-thiol protection, which is thermally stable. Up to almost, I think, 200 to 220, 250, that is the range of all these 4 nanoclusters. So with that, what we have seen, we have in direct co-reduction method, we have prepared silver 17, we have prepared silver 13, copper 4, the bimetallic, the AuAg16, these 2 bimetallic, and the trimetallic nanoclusters. And we have crystallized all 4 of them. So here, most of the people would have heard me saying all these things. Now I will introduce a little pinch of some more information. What I have seen in the crystals, these are the 4 crystals of these nanoclusters. What is the difference? Why I am showing this angle and things like that? So when we are trying to see the extinction of these nanocluster crystals, any crystal, see, when we are going to the microscope, taking any crystal, first of all, we will see if it's showing any extinction or the boundaries are sharp or not. So here I am proving that, and there is one drawback of this, because the cubic crystals will not show any extinction. That we have proved in our case also. The silver, the trimetallic one, which is cubic, whenever we are rotating at any angle, the same crystal, it is not showing any color change. Whereas if we are seeing all the other 3 crystals, taking this, anyone, whenever you are rotating it at any angle, 0 to 40, it is showing some color change. That is the proof that this is a single crystalline material. At the same time, all the 4 crystals are luminescent. I'm not talking about the solution. I'm talking about the crystal. The silver 17 and AuAg16 shows crystal induced luminescence. All the 4 crystals are luminescent with the prominent features at these particular wavelengths. The packing of these nanoclusters is obviously different. It is going from orthorhombic to this, say, trigonal and triclinic for bimetallic, and the cubic crystal system for the trimetallic nanocluster. This is the comparative UV, where we can see that, see, when it is silver 17, the feature is, main prominent feature is at 400. When gold is coming into picture, thus main peak is shifting to 385. We have observed it in AuAg16 as well as trimetallic, where gold is at the center. The prominent feature is 385. Whereas when copper is going to the peripheral position, there is no shift in UV. That means this particular peak is attributing from the central absorption, like central metal atom absorption. That we have already also proved with theoretical calculations as well. This is the mass spec of M17 nanoclusters. All the 4 nanoclusters, silver 17, AuAg16, silver 13, copper 4, and the trimetallic. We have also done the MSMS studies. What we have seen, the prominent feature what we have seen in MSMS studies is, whenever we are colliding it at higher collision energies, say 25 or something, the fragmentation, what is happening is, see, it is silver 17 with ligand 12. The fragmentation, what is happening is AgL2 is lost, and we are getting a corresponding 2 negative species of silver 16L10. Here, what we are saying, that the peripheral, the outer silver is getting lost with 2 ligands. How we will prove that? When gold is at the central position, we are seeing the loss of silver L2 only. But when copper is going to the peripheral position, we are seeing the loss of CuL2. That means, that also proves that copper is sitting at the peripheral position. Similar in the case of trimetallic, we are seeing CuL2 loss prominently with this corresponding two negative features. Now coming to the photoluminescence studies of these nanoclusters. See, silver 17, as I told you, all the crystals were luminescent, but silver 17 in solution at room temperature was not luminescent. A small hump at 650 was seen, whereas AuAg16 shows a prominent feature at near NIR region. When copper is coming into the picture, it is making the system luminescent. The silver 13 copper 4 is highly luminescent at 650 nanometer wavelength, and the emission spectra of trimetallic shows that it is highly luminescent as 610. See, what we are seeing here, as I told you, there we can easily find a difference just by looking these nanoclusters in UV or PL, in UV light. What is that difference? The silver 17 and gold silver 16. See, whenever gold is coming into picture, it is showing a shift from 400 to 385 in UV absorption spectra. But whenever copper is coming into picture, it is showing luminescence, difference in luminescence. So we can easily differentiate all these four nanoclusters by UV and PL. We need not to go for mass spec. We need not to go for any other characterization technique. Similarly, what we have seen, this silver 17 and AuAg16, when we are taking them at very low temperature, they are luminescent. We have also seen that silver 17 and AuAg16 are having crystal-induced luminescence as well. So I have a theory. I don't know whether I am right or wrong. There are some, in this silver 13 copper 4, as it is luminescent, there are some intramolecular transitions which are responsible for the luminescence in silver 13 copper 4. But in the case of silver 17 and AuAg16, there are some intercluster. There are two clusters. There is a transition between this cluster and this cluster, which is responsible for the origin of luminescence, originating luminescence. Why I am saying so? Because in crystal also we will see that all these things will be packed side by side by side by side. And that time we are seeing luminescence. Similarly, when we are freezing it, we are what we are doing, we are freezing the mobility of these nanoclusters. So transitions might happen from one nanocluster to other nanocluster. So that it might be the reason for this luminescence origination. When we have also seen done experiments to see the lifetime of what it is, fluorescence, phosphorescence. So showing that the silver 13 copper 4 as well as the trimetallic shows phosphorescence. We have also done this oxygen bubbling test. This is a funny test. If you will bubble oxygen for some time, and then you will see you will record the luminescence spectra again, it will quench. If it is phosphorescence, the triplet state will be quenched, and you will see the decrease in luminescence. Now we have the structure of all these four materials. We have crystallized them, we have characterized with UV, mass spec, and all the other techniques what we can do. We have done XPS, IR, all the supporting information I am not keeping. They are thermally stable up to 200 to 250 degrees centigrade. All these things, we need a theoretical explanation as well. So we correlated our data with the theoretical understanding, and Professor Hanu did the theoretical all these calculations, and they told us that the energetically best doping position for gold is the center of metal core that we have seen in single crystal X-ray diffraction as well. Similarly, they have also told that the energetically best position for copper is the peripheral one. So we are saying that these doping positions, we are exactly correlating with the theoretical data. Secondly, we have also correlated our absorption features of all the four nanoclusters. Although there was some deviation from this trimetallic, we were not able to explain properly what was this deviation from, because trimetallic systems are very complex systems. So this absorption and these things were deviating a little. There we have also correlated the band gap or the theoretical and experimental band gaps. Then we went to Professor K.V. Yadav for transient absorption studies, and what we found that all these four studies were done by Professor K.V. Yadav, and this is the decay kinetics what we are seeing, and Even the silver 13 copper 4 went outside the range of their experimental parameters, showing it more than 1.5 nanosecond of decay. Now coming to the summary and takeaway, I think I am well in time. Now coming to the summary and takeaway of this work is we have synthesized 4 materials, we have characterized, we have studied their properties, we have theoretically understood all the 4 materials. Now coming to the future perspective, what we can do in future with this material. I will show you a glance of 1 or 2 things. Even I have shown you in the our work presentations how we are using this nanocluster, all this M17 system. The copper which is at the peripheral position can be used for, and it is thermally stable. The most important point, it is thermally stable. It can be used for catalysis and these kind of applications. And we are doing that. So coming to the future of this, this paper was published in Nature Communication, and it came online on 30th January 2025, this year only. So what we have done, what we are doing next with this nanocluster, we have these 4 nanoclusters. Okay, I told you, we have synthesized this with the direct co-reduction method. Now we are also exploring the properties of metal exchange, showing these different 5 reactions. Another aspect is, here we can see the mass spec and PL change. The other aspect is using this nanocluster as a catalyst. As I showed you in the last Saturday presentation, this catalyst is able to break the CF bond activation, these kind of catalysis we are trying. And as I have this material in good quantities, nanocluster means in milligrams, not in grams. So as I have this like pure material in few milligrams, so we are exploring other possibilities with other people as well. I think people who are working in nanoclusters, almost all of you are doing something or the other with this nanocluster. Shweta Shri doing something, then Sujan doing SCRS, and Lopamudra seeing the aggregation-induced properties transformation. Harshita studying it with micro ED. Subrata Bagh started the applications in this electrochemical and photochemical applications. Not only our group, people from different parts of the world, say Professor Kappa's lab, they are interested in the IMS studies and gas phase behavior. The Professor Host Han, they've started doing something. And many other people from India, like Professor Meena Nemiwal, Professor Piyush Ghosh, Professor T. Palani Selvam, who is trying to use this material as a Ag17 anode composite for lithium all solid state battery. So being said this, I just want to show you that there is a huge potential in these 4 materials. And seeing that potential only, we have published this, say, structure-based paper, and now we are trying to explore each and every aspect in greater details. With that, I would like to thank my collaborators, which are most of them which are directly involved in this work, and which are indirectly involved, which are doing the further extension of this silver 17, this M17 work. First of all, thank you very much, sir, for always being supportive. My group, Pradeep Research Group, this includes most of the seniors. The junior people are not here. Apologies again for that. And acknowledgements to IIT Madras, the Department of Chemistry, my colleagues, family and friends, the Ministry of Education for my Prime Minister's Research Fellowship. Thank you very much, Deepak. I think I have taken exactly 25 minutes.
Yes. Thank you. Thank you so much for a very nice presentation. So the floor is now open for the discussion. Please ask question.
I have presented it multiple times in the group. So I believe there will be strong new questions. Sorry to interrupt. Who is this?
Vivek Bhaiya, you have shown that the photoluminescence is coming at 610 nanometer and the UV absorption maxima at 380 nanometer, right?
Yes.
In your slides.
Yes.
So why this much large stroke shifts is there? Like what is the reason in this particular nanocluster?
We can't say exactly the reason of this stock shift, but
It is quite large.
yeah, it's quite large, and usually it's not expected. I don't know. I don't have a proper explanation why this particular nanocluster is behaving like that. Because in nanoclusters, these things are totally not predictable. That where this emission will come, where this absorption features.
Since
I
you have the
don't have-
theoretical idea about the energy states, so we can predict that what type of any trap states or some what type of
Yes.
states are
See, we
associated.
have the overall. If we will go for each and every feature of absorption, we have the calculations for only AG17. We don't have the whole calculation part for AU-AG16, AG13 copper 4 and the trimetallic system. If we will take each and every band, that is not there for these three systems, but for AG17 we have. So yeah, if we will go for the details of theoretical calculations, yeah, we can predict that.
Let me come in here for a minute. Samapti, you asked a very important question. So in general, all nanoclusters have this large Stokes shift. And that is even more evident in the case of protein-protected clusters, where a typical protein excitation falls in the, well, somewhere in 200, 260, 300 region. Now emission is in the near infrared. Large Stokes shifts are very interesting because there is no overlap with excitation. So the question would be the origin of large Stokes shift in clusters in general. Nothing particularly about Vivek's cluster, but any cluster that we have looked at, there is a large Stokes shift. Now coming to the point, this can be a subject of a PhD, right? This is a very interesting subject to look at over a range of systems. But one thing that is obvious, that is the largest absorption cross-sections that you are having, they are computed. That is why you have the optical absorption spectrum. And largest absorption cross-sections are somewhere in the range of whatever 300, 400, depending on the type of cluster that you're having to do with interface states. Now, it is also clear that the band gap is somewhere in the 600 regime in all systems. Very, very, very shifted. Now, we also know that there is a very large energy relaxation that happens in the cluster systems. So you excite at the interface, but you have extremely fast relaxation because the interface is communicating. It's almost like a net. It is a net of, let's say, cobweb. So anywhere you touch it, the web is energy relaxation is quite fast in this system. After this relaxation only, the luminescence occurs. So somehow the energy relaxation time scale is the issue here. That energy relaxation time scale is what our people like Adarsh are looking at. They're the best, very best. So coming to the answer to this question, studying the energy relaxation mechanisms across a number of clusters would give an answer to your question, and a very important question.
Yeah, I got it. Thank you, sir.
Thank you, sir, for explaining. And thank you, Samapti, for a great question.
Sir, isn't there a possibility of this coupling between these low energy phonons? I have read somewhere that there is a possibility of like self-trapped excitons kind of thing. Whether that's also one of the causes?
Yeah, a very important point, but it's also important to examine that aspect in the solid state. So whether these excitations do, not necessarily the intramolecular vibrations. In the solid state, the intercluster vibrations, to what extent they are also involved in it, that is essentially that's what you mean by phonons.
Right, sir. Yeah.
So Vivek, let me just get this started with something provocative. Can you please put your overall cluster, all the 4 clusters and their beautiful rotations?
Yeah, yes, sir. Is it visible?
No, somehow this
I think Vivek,
presentation
you
is
have to
black.
reshare.
Oh, I will reshare it. Just give me a moment. I will share the whole desktop. Is it
Don't
visible
share.
now?
Yeah, good. So now comes, one of this is a sphere, right? Very nice sphere. And each carborane is also a sphere. And thinking through, these carboranes are all rotating, right? They are all rotating. And at one point in time, they will freeze. The rotations will freeze. And the rotations in general are frozen in the solid state. That is how you are resolving the structures and things. And there may be some kind of a rotational anisotropy, whatever. So all this is there. Now comes the question, boron is a great NMR nucleus, right? So there is a great NMR question here as to when would the rotations freeze of the carborane. Now, if you can look at it, that's a great question, because after all these plenty of borons, great signal, and dear Deepak has all that NMR data and all that stuff. So there is no difficulty in getting this quality NMR. So question is, when will it freeze, right? So that to me is going to be a rotational freezing, right? It's a rotational freezing that you can see. But when you start freezing, it's also possible that some rotations will freeze faster than others or earlier than others. In this particular case, all are symmetry equivalent maybe. In some other cluster system of carboranes and others, rotations are different because symmetry positions are different. I'm bringing up this issue. Now, you also see that there is carbon. Huh? The carbon is also fellow, that's part of it. They are also rotating, whatever, right? Now, you can see this carbon boron changes and this energy you are having the interaction, hyperfine interactions between these. So all these are interesting things to look at. When you start looking at it, even more exciting things come up. For example, C60, you ask this question, how the C60 was formed. You're talking about one position number 1 is now functionalized. C60 also, position 1 is functionalized, let us say a bromo something. Now the next fellow that is functionalized can be in very different positions. You create many isomers, which give you different kinds of carbons and different kinds of NMR frequencies, which differently freeze. You also then ask this very complicated question as to how C60, one carbon, is actually communicating with the other communicating meaning the magnetic interactions, how are they communicating? This is getting us information as to how aromaticity is, C60 is a pseudo-aromatic system. How can this be communicating? So there are very complicated, extremely interesting questions in NMR. And this is probably an interesting system to look at NMR.
Yes. but we have to be really very precise when
Yeah.
we are looking for these kind of things. Yeah, but it can be explored.
No, we have enough intensities.
Mm.
That's a good thing about it, right? Because quite unlike other nuclei, here we have plenty of signal, right? Because all the intensity is there for you to look at.
Yes.
Of course, silver is also NMR active, but then I'm not talking about the silver. And the boron signals are, of course, you also have boron, carbon, and hydrogen. All of them are.
Mm.
Okay. So I'll
So
just
do
stop here. I'll come back later. Okay. Yeah.
Yeah.
Just somebody asked, Deepak, did you ask something? Or?
I think people are seeing this presentation for, I think, nth time. So
Anyone else have some question?
Yeah. So Vivek, can I go ahead?
yeah, please.
Okay. So when you are talking about this mass spec of AG17, I can see, can you go to the slide itself where you have done the study with collision energy also?
Yeah.
Yeah. So if you are seeing this on the last mass spec also, I can see there is a peak in the parent spectrum also around 1740.04, which is probably for the AG16 L10 2 minus. That you can see, like if you are going back to the first mass spec when you talked about, you can see there is a peak around 1740.
The very first mass spec.
Yeah, of AG17.
Are you able to see it? AG17 or AU AG16?
No, AG17. I can see a peak around 1740.
I'm so sorry, this slide I will slowly go.
Yeah, this one. Perfect. So as you can see, so the first one is around 1312.42, which is your AG17 3 minus. Then if you are seeing there is a small peak, which probably is around 1740, which is for your AG16L 10 2 minus. Is it so?
No, actually, we have not
Okay.
seen any fragmented peaks of this AG16 and L10. This might be some impurity or some other thing, but that was not present here precisely. It was
Okay,
that.
just have a look on that. Like probably I feel that is around 1740 and probably that is for AG16 L10 2 minus. Just have a
Yeah,
look. Yeah.
we have to have a look. I think it's not there in the final spectra.
Sorry. The peak you are talking about, 1700, around 1740, it is corresponding to AG16 L10 2 minus. But I think this is a spectrum which he showed. That
That
is
was
not,
crude one, right?
yes,
Crude
that is
one,
a,
yes.
See,
Yeah.
in the final spectrum,
yeah.
we have vector spectrum for that too.
And
No,
in the
God.
AG17 mass spec, this is copper
Small
exchange
hum.
peak.
Yeah, we have to look it in more details. Yeah, you are right. We can look into it.
I think Samapti is asking something.
This AG17, this bottom spectrum, is it the copper exchange peak, this small hump?
No, that is not the copper exchange peak. That is a complex which is getting formed in this
Okay,
system.
that 13.8, right?
One.
1 minus.
Yeah, 1 minus peak.
Okay.
That
Yeah,
is
so
just
we were
this one, right?
we were also struggling when I tried to check this gold nano triangle plus AG17. We were getting something like that.
Yes. Yes,
Yeah.
even when we are trying this metal exchange or some things like that, sometimes this peak will be prominent. That depends on the purity of the sample. So this
Bhaiya,
is one negative.
in some absorption spectra, this is looking like there are some features. Is it any instrumental error or like
Which one? This one?
No, like UV visible. Go
Yeah.
back.
Can you see the
This
slide?
kind of.
These kind of features. See,
Mhm.
the lamp is changing at around this 360. So whatever these things are, I will attribute them as peaks. this cannot be an instrumental error, because if it is so, it should be in all the other cases as well. That's why I was saying the trimetallic, this was very complex, some hum kind of thing.
Can you go back to other slide, previous slides?
Uh,
Here.
this?
This absorption P, this 400, it has some
No,
like
this is not. This is at a lower scan rate. This is at a lower scan rate. That's all. These are not the humps. This is a C. I am telling you, whenever I'm doing crude samples and those kind of things, just to like save time, I will go for these kind of parameters. And this is the progress what I was showing you. This is the final spectra. You will change the scan rate when you just want to see whether the things are formed or not. You can play with these scan rate kind of things. Here, see, there are no such humps or kind of that.
Okay, I understood.
Yeah.
I have another one. So when you are talking about this Ag17 luminescence at 77 Kelvin, I can see it's kind of a bioluminescent material. If you go back, yeah. So is it so? If you can see, there is a hump. So is it like the bioluminescence, like probably involving a singlet and long-lived triplet emission? Like,
Sujan,
had you seen?
Yeah, I have seen this hump, but we have not observed these thing in very great detail. Like, see, this experiment, how we did it in RPL. To be truthful, we did it in RPL,
I
just
can
putting it
understand.
in liquid nitrogen, and this is not temperature dependent PL what we have done. For answering your question, we have to do a systematic study how this is changing by changing temperature. This is a like funny experiment what me and Arijit did just by putting it in liquid nitrogen, our sample in liquid nitrogen.
Right. No, as you were mentioning that I believe in lower temperature, you mentioned intercluster, some kind of communication is happening, right? So
That's
that
what.
would be very, yeah.
See, there is no proof for that. As I
No,
mentioned,
that
there
would
is
be
no
interesting.
proof for
Exactly.
that.
Like if you can trigger this thing, that would be really interesting. You can
Yes.
prove your point.
We need a very high computational support for like proving this theory.
Right. Okay, perfect. Thank you, Vivek.
Yeah, thank you.
I have one question, Vivek. Can you go to the back, previous slide?
This luminescence?
Yes. So continuing the Sujan question, the figure E having the hump. So have you seen this figure G where multi-component or single component you got?
This is a
Dictate.
multi-component. This is a 3-component.
So
Silver
from there
17
you can
is
explain
3-component.
how many components? Three.
3-component. Silver 17 is 3-component, whereas AUAG16 was 2, whereas the
From there, can you explain the figure, whatever Sujan is asking? Because that relaxation can correlate what is the slight hump is there.
Yeah,
Maybe
try to
hump.
right. Try to see the time from there so that you can explain this E in a better manner, I believe.
And
Thanks,
also,
Deepak, for bringing that up. Yeah.
and also in the figure B, when the gold is doping in the center, it's showing the 815 nanometer. It's very, why it is happening? Because if the gold is going on the core, the same thing I will expect when the gold and copper is there, but it's not happening in figure D.
Yes, we have not seen this greater hump of 815 in the trimetallic system. This spectra, we have collected many more spectra, although this is not showing 815, but still this is not showing any hump there. That was surprising for me as well. I have taken many spectras in details, but there was no hump in the trimetallic. That was strange. And really, I don't have a proper explanation for that. I tried, that was a question originated for me as well. So those experiments were done in greater detail, but we didn't see that.
Okay. So any other question?
I think sir will be having.
Yeah, I do have some questions. I'm just waiting for people to ask. Okay, So I wanted to say that these presentations, the reason why we are doing these presentations, as I have said this before, for the benefit of people who have some reluctance and all that, let me say this once again. The key aspect of this presentation is to ensure that our people have capacity to stand before others. And this capacity to stand before others is the sole reason for anybody to get a job. And this does not come from nothing. It comes from continuous effort. And for that, it is important on the part of the speaker as well as from the part of the listener to improve the presentation capacity. So one should ask very penetrating questions, original questions that are not there. So questions are not like instead of methanol, why not we use propanol, you know? Questions should be deeper. At the same time, answers should be deeper too. This way, it helps everybody. So I wanted you to think it over. And it may not be possible for everyone to come up with original questions quickly, but it is important to ask those questions. And secondly, if you have published something, you should be in a position to stand before people. So I do not like anyone saying, oh, you know, I can't do it. I just don't like it, because it only says that you are unprepared. Okay, so having said this, so if you have questions, go ahead and ask those questions. I will wait for another minute or two.
Vivek,
Yeah, you ask that.
I want to ask a question. Like, although I know we are trying to dope other metal systems in AG17, and we have seen only +1 oxidation state metals in the same group, gold and copper is getting doped to this system and not other metals. Do you have any clarity for that? Why not group 1 metals or any other +1 oxidation state metals, or metals having same size of silver gold, why they are not getting doped in it?
See, I have recently started trying for other metal systems which are in +1 state. So, to be truthful, this is a deep question. Even few hours ago, it was asked in my PMRF review as well at 3 o'clock today. So, the answer is why +1 is going inside and
Vivek.
+3 is not going inside.
Vivek,
Uh,
the reason is maybe the nickel, palladium, platinum interacts with the DPP which you give into your reaction. That
Not
forms a complex immediately.
a rigid answer is there right now from my side, but yeah, we have explored n number of things. Am I audible, right?
Vivek,
Sorry, Amog. Sorry, I muted myself so that.
no, it's
Yeah.
fine, it's fine.
Yes,
The
yes.
reason what I think might be is nickel, palladium, platinum you have tried, right?
They all were not in one, Amog.
No, yeah, but even the +1 oxidation state which you are talking about is which metals?
Which metals? That is gold. Gold, when we are trying with +1, it is showing metal exchange, but with HAuCl4, it is not showing metal exchange. And secondly, I'm trying to prepare few complexes. That will be a very complex soup, but I'm still trying to prepare some complexes with +1 oxidation state, getting motivated from the inorganic systems, what people are preparing.
Yeah,
But still,
maybe I misunderstood the question.
Yeah, her question is why only 1 plus is going inside, not 3 plus, the same metal, and why other metals are not going inside. So for that, there is no concrete answer from my side. These are the observations what we have
Have,
observed together.
have you tried AUDPP complex?
Yeah, that's
That's
what
plus
what
one.
it is going inside.
That is plus one,
And
and even the there is plus three and plus one. Both AUDPP complexes are there.
we have tried with +1 then, and it is really going inside and in metal exchange, not particularly in this work. When we are directly using it in co-reduction, gold doesn't matter what is its oxidation state. It is going with HAuCl4 as well. But for other metals, it is not going. So that is a question. But no concrete answer. Sorry. We have to explore more, I think. Yeah. If anyone has any idea regarding this, please feel free to answer. Please feel free to for this discussion.
Okay. If you
Vivek,
start, yeah,
Yeah.
I
go
have
ahead.
one question. Like in the Ag17 structure, the central Ag atom is totally locked in this Q octahedron structure. So how that site is becoming accessible to the gold?
To the gold, that is a great question, and we will be probably trying to answer this question in our metal exchange system when we will be showing this metal exchange. The one of the slide I told you, not direct co-reduction, the metal exchange, how we are making this bimetallic and trimetallic. There are reports where people have shown that this. I always used to show one of the report where people say this icosahedral will form a cage kind of thing. It will open little bit and the metal will exchange from there. But that question properly we have to answer, and we are aiming for that only because
But Vivek, there is also another report where center atom tunneling happens through the core of Ag12, that's icosaedral core, where the gold first sits on the Ag12 core, then it is tunneled into the central
yes.
position.
Yes. For this 17 system, we want to calculate that only, that we are adding gold. So whether it is replacing the outer peripheral one, then replacing the icosahedral, then going inside, or how this thing is happening. So
You are
there
saying
are
a metal hopping there?
what metal?
Like hopping of the metal from periphery to center.
We have not observed yet. We have not
Yeah,
seen.
it's
Sir was also we were discussing few days back for this metal exchange, how this copper is going to this icosahedral or not, that exchanges are happening, continuous exchanges are happening or not. We are yet to answer these type of questions.
And for the perspective of this doping, so what is the electron count of the Ag17? That is a magic number.
Yes.
So
See,
yeah. So let me just finish. So the Ag17, if has a magic number, so it is quite stable. So how does doping come in the picture for the stable cluster? Like what is the driving force to get doped with another metal?
that Professor Hanu has explained it,
One
showing
thing
that
may be higher entropy.
yes. And they are showing that if gold is replaced from silver at the center position, the energies, the differences in energies for each particular position. So when gold is sitting there, that is more favorable. Entropy is the key.
Also, one of the major parameters is E0 values shown. So we have to consider what are the E0 values for the reduction to happen. Whether this gold, which like the silver which is present, if it is coming out as, let's say, silver 1, and gold 1 is going to gold 0, what are the changes in the E0 values? Whether you are getting a delta G negative for that. Delta G is equal to minus NF E0, right? So it's a complicated matter of various parameters: thermodynamics, kinetics, your E0 values, electrochemistry. You have to see a lot of parameters to really come to a conclusion that whether the doping will happen or not.
And really, nanocluster chemistry, all these parameters can be calculated by theoreticians like Professor Hanu. Like at our stage, we are not in a position to comment particularly. They are not molecules, they are some bigger entities with like some hundreds of atoms.
I want to comment on. Oh, sorry. I want to comment on the question asked by Soham about the gold doping. In literature, the paper we Amok talked about that gold atom diffusion to the AG25 cluster, it happened over a 15 minutes time period. But here, when we are seeing the reaction, studying the reaction of AG17 with gold complex, it is happening with a very fast time scale. We are not observing its doping on the core. Within minutes, we are not seeing any cross-sectional changes over time.
Yeah, even
But
Shweta, you would have seen. Sorry, Amol.
but one atom doping, can you differentiate if it's in center or in the core through mass spec?
Yes, exactly.
It's from not.
Yes.
Not from mass spec, but
Okay.
from IMS studies.
Okay.
Like they have seen the doping and diffusion of the gold atom happening in the AG25 system over a time period of 15 minutes. But when we have also performed similar type of experiment, but we have not seen it is here in this case, the doping is happening within minutes, and we are not seeing any changes with time.
Yeah, but one thing is the clusters energy gaps should also be taken into consideration, because the AG25 might have a different energy gap or energy levels, which may be affecting the scale of the reaction, time scale of the reaction. Maybe it is not occurring in 15 minutes, but in 15 seconds, but the route is the same.
Yes, that can happen, and that is what I was indicating, that it may not be metal hopping to the center. It may be happening from diffusion, but we are not observing it.
Even Sujan
Maybe
sent
a very
something
fast time
in the
scale.
chat.
But the
Yeah, so
from mass spec data, can you infer about like it is staying in the interstitial site or occupying the core or where it is sitting? You can't predict the site, right?
In IMS, she told, right? We
Yes.
can do that through that path, like how much time it takes for that cluster to go.
Okay. Okay.
yeah, so time is running out, and so a few more questions are probably important to ask or maybe to mention. One
Bhaiya,
aspect.
can I ask one question?
Oh, yeah, please go ahead.
Good.
Bhaiya, in your case and in many of the nanoclusters case, we have seen that copper is occupying the outer positions. But in my case, the nanocluster which I synthesized, I am observing that copper is occupying the inside position. Like, could you give me some like idea or any suggestion why it is occupying the inner states?
See, that is probably Yeah, Amol,
Ca-
you were saying.
Can I add one point? I
Yeah,
want to
please.
ask
Yes, yes.
Harshita a question. In your cluster,
yes.
it is like not only metal, but metal sulfide, right?
Yes.
So that's the thing.
Silver
Like it's
sulfur
not
is outside and
uh,
copper is inside.
sulfide is there with copper.
Silver sulfide
Sul
is outer side.
No, I'm asking if sulfur atom is also there in the core.
No.
No,
Okay.
it's not there in the core.
Completely, structure is completely solved, right?
No, not yet. We are still working
Okay.
on it, but this we have observed till now. So I
But
was having
sulfides are not
doubt,
there.
like what
That
could be the
is,
reason?
Okay. I thought maybe the sulfide is present in the core. Then we can talk about the oxidation states. The position is easy accessibility for the ligand. That's how the
But in
position depends.
Yes, but
Okay.
in that case, in that structure, Amog, sulfides are not present inside the, like with the metal core. So in that case, why copper is going inside is a question. And Harshita, this is the preferable position of copper. What we are seeing, like seeing 20 examples, 17 is going there. But 3, it is still, there are some examples where copper is going inside. So there are no particular literature or there are no particular insights stating that what will be the position. That's why I was telling you these complex answers can be given theoretically. And theoretically, it is given for particularly this system, energy, and you see gap and things. Copper is favorable for the peripheral position. So there are many factors which are contributing to for this preferable position, but we can't generalize this thing that copper will definitely go at the peripheral positions. This is not a generalized statement. This is a statement what we are seeing with some 10, 15 examples, say. But there are more examples which shows copper is going inside.
Okay.
Also,
Thank
Harshita,
you.
sir, one last
Yes,
point.
sir.
Yeah, if we do a careful XPS study of your cluster, maybe we can correctly predict why it is going inside and why the silver is outside. That also we can do.
We will do that.
That's all.
Thank you.
So the other, when you start thinking about looking at these clusters in greater detail, can you put back your original cluster? Yes. So the reason why I'm asking these question is because I would like people to look at their own structures and research from different perspectives. This whole subject of atomically precise clusters is a lot of connections to monolayers, self-assembled monolayers. And their silver sulfur carbon bond is very different from gold sulfur carbon bond. Now, silver sulfur carbon, that is what you have in silver monolayers or in gold corresponding gold angle. Gold angle is generally sp3. Silver angle is generally sp, meaning it is closer to something like 180 degrees, whereas this gold is somewhere close to 110, 115 some degrees. So here in your particular case, if you look at AgSc bond, it is more towards sp3. More, as you can see, the angles are like that. Now, I wonder whether the chemical bond angles are of atomically precise cluster systems have been looked at in that detail from that structural angle. Suraj is looking at some correlations and things, but I'm saying that clusters of gold and silver systems, what happens to their angles as the let us say as the nuclearity changes, as the ligands change. Now, if you look at the gold sulfur carbon bond, which is 180 degrees, they are generally weaker bonds. Not the gold, I'm sorry. Gold sulfur carbon bonds are stronger in comparison to silver sulfur carbon bonds in monolayers, which one may generalize by saying the bond angles and the orbitals involved. Here, the strength is probably related to that argument. That is, it is more closer to sp3, not sp. So now I don't know to what extent these angles are different in other carboranes and how that is related to the bond strengths, how that is related to thermal stability. So there is let us say these 500 clusters or whatever number of clusters that we have today, and if we can correlate all of them, something new is out there, similar to this issue of the large Stokes shift. So that's the other larger thing that I wanted to mention for people to think about. We've exceeded our limit. So we should move to the conclusion. And Deepak, please go ahead.
Thank you. Thank you so much, everyone. And thank you, Vivek, for very nice presentation and discussion. So we will meet again next month. I will share the details of the speakers. So see you again.
Deepak, I have a suggestion to add. Please announce it prior, because it was
very important.
yesterday and today was my PMRF review, so it was difficult for me to manage time. I got only 2.5 to 3 hours for this presentation preparation.
Yeah, because of the sir traveling and others, previous some confusion between you and Vijay, so it got delay. So that was some previous confusion from you people also.
Yeah, because it's really hard to make a presentation.
Anyway, now you see we have some whatever number of people of published papers this year. Make a list.
Yes,
make a list.
I'm following the list or whatever the.
Whoever wants to present, don't push anybody. If somebody doesn't want to present, leave that person.
Yes.
Okay, that is up to that individual. You may decide not to. I mean, you don't want a job. You don't want a postdoc. You don't want anything. So there are people like that. There are people who have multiple postdocs anyway. So there are multiple jobs anyway. There are people of different kinds So it doesn't matter. We should take a very positive view about it. That is, this is a way to enhance yourself. And it is not 37 people here, 35 now, 1 hour each is a significant amount of time that others are investing on you. Right? Thank you.
Thank you, everyone.
Thank you, everyone.